Hi everyone, I'm Chris Hine. I'm a developer advocate for Kubernetes and EKS at Amazon Web Services. Today we're going to be talking about running Kubernetes on Amazon EKS. Kubernetes offers a powerful abstraction layer for managing containerized infrastructure. Amazon Elastic Container Service for Kubernetes, EKS, makes it easy to run Kubernetes without having to manage the control plane or etcd operations. In this session, we'll show how to deploy an Amazon EKS cluster, how to deploy some containers onto that cluster, and we'll talk about some of the tools that make running containers on EKS easy. First, what is Kubernetes? Kubernetes has been around for a few years now, almost 4 years of being generally available, and it has absolutely taken the world by storm for running containers, especially over the last 2 years. It's also gained rapid traction amongst AWS customers. So if we strip away the hype, at its core, Kubernetes is an open source container management platform. It helps you run containers at scale and gives you building blocks and primitives for building modern applications. Our customers believe that there's tremendous advantages of running Kubernetes on AWS. According to the last CNCF survey, 57% of Kubernetes workloads run on AWS. And this is one of the reasons why we created Amazon EKS. Amazon EKS is a managed control plane, which means all you need to manage is the worker nodes your applications are running on, and we handle managing the API server, the cloud controller manager, the scheduler, and etcd, the persistent storage used by Kubernetes. When you create an EKS cluster, you'll be given a CNAME like this. This CNAME represents the ID of your cluster, and when you deploy your worker nodes, they'll connect into this cluster by connecting directly to that CNAME. And when you want to actually connect into it, you'll configure a Kubernetes config file or kube-config file. And that kube-config file will then be referenced by the command line tool for Kubernetes called kubectl or kube-control. This CNAME represents the managed control plane for your EKS cluster and allows you to send operations which would tell Kubernetes to schedule containers for you. When you create an EKS cluster, it actually goes through a couple steps. The first thing that you're going to want to do is you're going to set up your environment. And by setting up your environment, you're deploying things like a VPC, a subnet, internet gateways, and any of the underlying functionality that is necessary to make your EKS cluster work. We provide CloudFormation templates in our Getting Started guide, which help you to get up and running. After that, you'll create an EKS cluster. And this is the actual highly available control plane. It'll configure all of the private key infrastructure. It'll set up the ingress into that control plane, and it'll give you that CNAME. Once this is done, you can provision your worker nodes. These instances live within your EC2 console and are managed by an auto-scaling group that you are able to control. This means that you can easily grow and shrink the cluster to your own needs. And then once your worker nodes are up, you can deploy any container you'd like, any operator you'd like. You have full control over how you build your applications on top of this cluster. So how do you actually get started? We've made it incredibly simple to deploy your cluster and all the resources using AWS's CloudFormation. We'll show a little bit more about this in a minute. You can also use a tool called EKS-CTL, which was built in partnership with Weaveworks, and it's a CLI tool that you can use that will automatically provision your clusters for you. or you can use any number of partner solutions, such as Terraform, Pulumi, or Rancher, to deploy clusters from those tools. AWS CloudFormation provides the AWS native way to provision clusters. It's simple to manage via the CLI or using the AWS console. You can quickly replicate your clusters across multiple regions by using the same templates. And you're able to track any changes using the newer drift functionality to these clusters. This is a slice of what a CloudFormation template looks like to deploy an EKS cluster. There's some other components that go into it, for example, the VPC and the subnets that you'll typically have in the same template. But this is what it takes to actually deploy just that base. If you'd like to scan the QR code in the corner, that'll take you to the Getting Started guide where you can take a look at all of the CloudFormation templates and how to get started. Another way of provisioning clusters is to use EKS Cuddle. EKS CTL provides a single command to create, update, or delete an EKS cluster. As I said before, this was built in partnership with Weaveworks, and it features a very simple configuration file, which is highly customizable. You can do anything from automatically configuring IAM policies for cluster add-ons, like the cluster autoscaler, or even deploying multiple node groups that have different instance types depending on your workloads. Given that it's a single command, all you have to do is run the command EKS-CTL create cluster and wait for the cluster to come up. Once that's done, you'll be provided a kubeconfig file that will automatically allow you to connect into your cluster. It was built using the GitOps. You can actually store these configuration files in a Git repository and then set up a CI/CD process that automatically will re-provision the cluster if any issues happen. If you'd like to see more information about this, you can scan the QR code in the corner. And lastly, we have partner solutions and open source tools like Terraform, Pulumi, or Rancher, which all allow you to deploy EKS clusters today as well. And depending on how your organization typically provisions infrastructure, you can choose the best choice for you. Each QR code will take you to the documentation for deploying, for example, the Terraform EKS provider, the Pulumi EKS deployment scripts, or even the Rancher documentation for EKS. Okay, so now let's switch to a quick demo. I'm going to provision a cluster and show how easy it is to get started using EKS. In this demo, we're going to deploy a cluster using EKS-CTL, and I will show you the config file that we have to actually deploy this cluster. In this directory, you'll see that I have a file called cluster.yaml, and this cluster.yaml defines how the cluster is actually going to be set up. So we're passing in a name of K8s on EKS-Pro. We're going to do this in the US East 1 region. And I'm configuring a node group which has a name of NG1, an instance type that gets spread across that of M5 larges. And I'm going to have it deploy 2 of those. And I'm going to default to having private networking set to false. And then each one of my instances is going to automatically allow me to SSH into those instances. So to do this, we're going to run EKS-CTL create cluster -f cluster.yaml. And because I like to manage my config files directly in the same project directory, I'm going to pass in kubeconfig to kubeconfig. Now you can see that this cluster is being brought up. It's already set up my subnets for US East 1D. You'll see that it's using this AMI, and it's deployed my SSH keys automatically in so that I can SSH into those nodes. and it's starting to create this stack. This process is going to take about 15 minutes. So while this goes on, let's go talk about some open source tools that help you to deploy and run Kubernetes on AWS. So here's a couple projects that will help you run and deploy containers on top of EKS. These are all open source projects that the EKS team has been contributing to or building. We're going to talk about a couple CSI drivers and what CSI drivers actually are. We'll talk about the aws-iam-authenticator. We'll talk about the aws-alb-ingress-controller. And then we might talk about some other things, and we're going to deploy some containers at the end. So first up is the CSI drivers. And these CSI drivers work for our EBS, EFS, and FSX storage solutions. But first, what is a CSI driver? CSI stands for Container Storage Interface. It's a specification that allows storage providers such as AWS the ability to develop a plugin and have it work across any container orchestration platform. So for this conversation, this means we can provide a native experience for using EBS, EFS, and FSX with your EKS clusters. So the first one we'll talk about is the EBS CSI driver. And this is currently in alpha support and something we're actively working on. It helps you to manage your elastic block store based storage with your EKS cluster. So it'll automatically provision those volumes and mount them into the EC2 instances, and then attach that storage directly to the containers when you reference them. This is a great tool for a lot of different workloads, such as running stateful services like databases, where you might need high I/O. If you want to scan the QR code in the corner, you can get more details on this project. Next, we're going to be talking about our EFS CSI driver. EFS, or Elastic File System, is a fully NFS compatible service. And the CSI driver allows you to natively mount NFS-backed volumes into your pods, similar to the EBS implementation, removing the manual work of setting everything up. This again is in alpha, supports connecting those volumes and attaching those volumes directly to your containers. And this is really great for things where a pod could be scheduled onto any node in the cluster. I've used these in the past for deploying things like a CI/CD platform, and you can scan the QR code in the corner to get more information on this. Last of our CSI drivers is the CSI driver for FSX. This provides access to leverage fully managed Lustre file systems directly from your Kubernetes cluster. This is really great for compute-intensive workloads such as HPC, or high performance computing, machine learning, or media data processing workflows. With FSX CSI driver, you can use persistent volumes, which are automatically mounted into your containers and backed by that Lustre file system. Again, you can scan the QR code in the corner to get more information on this. The next project I want to talk about is the AWS IAM-authenticator. This project is maintained by Matt Moyer and Nick Turner and Matt Landis. If you want to view the actual project page, you can scan the QR code in the corner. So what does it do? The AWS IAM-authenticator provides Amazon-based authentication for your Kubernetes cluster. So in a typical Kubernetes cluster, authentication is handled in many different ways. You can have X509 certificates, which are used to actually do mutual authentication between whatever clients are trying to connect into the API server. You can use static tokens, which are stored on the file system that are referenced and able to handle the authentication, basically checking to see if a token exists. You can also use password files, so files on the control plane nodes that are looked into to find out if a password exists. You can also use service account tokens, which are stored in etcd, the persistent layer. You can also use OIDC tokens or webhook authentication. And webhook authentication is the mechanism we actually use to leverage the aws-iam-authenticator. But before we move on, it's important to actually classify the difference between authentication and authorization and what we are talking about here. So what does authentication actually mean? Authentication is the physical allowing of users or a system to access resources within the cluster. For example, how I could connect to my cluster and get a list of pods that are deployed, but it does not mean authorization, meaning if I have the correct permissions to actually list those pods. To do that, we actually leverage the built-in Kubernetes RBAC. So how does it work under the hood? The AWS IAM Authenticator works by using an external binary which you install onto your machine and is automatically installed onto all of the worker nodes. This binary is responsible for generating the token that is sent to the Kubernetes API server. When you make a request from kubectl or kubelet or any custom code, the client Go libraries will execute the binary and optionally assume a role, all using the AWS credentials that are on the machine. It then generates a token and adds that token into the request as a bearer token. This is the actual code that is used to generate that token. It's fairly simple, but it involves base64 encoding a URL, which is a request to the AWS APIs. That URL actually will return back the user that made the request, but nothing more than that. So this is how the full flow looks. When a client makes a request, it calls the local AWS IAM Authenticator binary to generate the token. Once the token is generated, it adds that as the bearer token header and makes the request to the API server. The API server then makes a request to a pod running in the control plane, specifically the AWS IAM Authenticator server binary, and that takes the token, parses it, completing the request to the AWS STS API to validate who the user is that's making the request, and it returns back a true or false to the API server for whether that user is authenticated. The last project that we're going to talk about is the AWS ALB-ingress-controller. And this is maintained by Yang on the EKS team, Craig and Andrew. You can scan the QR code in the corner for more details on this. But what does ALB-ingress-controller actually do? It provides Kubernetes ingress into your application using Amazon Application Load Balancers, or ALBs. Now, when we talk about ingress into Kubernetes, there's two different types that we're actually talking about here. There's typically services and there's ingress. Now, a service is anything that could be L4 or L7 type networking services. A lot of the times you'll see these referenced as type load balancer, meaning that they're actually going to reach out to the AWS APIs and provision an NLB or an ELB for you. When you do these, you typically expose a single service at a time. Ingress, on the other hand, is L7 only and has many different permutations. For example, ALB, the ingress, or ALB ingress, the Nginx ingress. You can use this with Envoy and a lot of other solutions. And what it does is it provides you more customization into how you actually route into your applications. So for example, you can use host or path-based routing in these and route to multiple services behind the scenes. So this is an example of what an ingress resource actually looks like. You'll see it's very simple. It looks like a standard Kubernetes manifest file. It has any number of rules under that ingress that can represent different paths. For example, this ingress is a test ingress. It's internet facing, meaning the ALB is exposed to the world and you can route directly to this. The rule that we have set up here says that any request going to /test path is going to be routed to the backend service of test on a port of 80. So internally in this Kubernetes cluster, we have an application that is exposed at test on port 80, and all requests to this path get routed directly to that container. Now that you understand the basic concepts, this gives you a better understanding of how the actual architecture looks. Here we have an ALB with 2 listeners, and each listener has its own set of target groups. When requests are made to that ALB, the listener has those rules. Remember, those are the paths that we were just talking about. And when a request is made through those, they get routed directly to whichever target groups are supposed to handle those specific requests. All right, now we're going to demo deploying some applications into our EKS cluster. As you can see, this EKS cluster is still being provisioned. It can sometimes take up to 15 minutes to actually deploy a cluster using EKS CTL. So I have another tab here that has a cluster already provisioned. You'll see that we can do kubectl get all namespaces. And you'll see this cluster has mostly default services deployed into it. Things, for example, our core DNS pods, which handle internal traffic and DNS records. We have our kube proxy instances that are deployed onto each node. We have our CNI driver already deployed into it. And then I've deployed a load balancer into this because those can take a couple minutes to provision as well. So if I clear this, I'm going to then open up my manifest file. So the applications that we're actually going to be deploying are 3 different containers. So in this, we have a service, like we were talking about during the presentation about ingress versus services. And this service is exposing an application called Tracks on port 4567. And the actual application that's exposing is this deployment. So this deployment is taking an image called MX Tracks and exposing it again on 4567. And when a request is made to the DNS record Tracks, it'll automatically get routed to this deployment. Similarly, I have another service and deployment called lap times. And then I have a web app service, which this one's a little bit different, where it exposes 2 different ports of 80 and 443, and also deploys as a type load balancer. So the other 2 services were actually cluster IP, meaning they're only exposed on the internal system. This is provisioning an ELB, which again I already provisioned for us, and it exposes the web app deployment on that port 80 and 443. And we pass in a couple environment variables so that the web application can actually connect into the subsequent microservices behind the scenes. So this application will talk to the Tracks API and the lap times API so that it can present a web view of what those look like. Very simple application, but we can deploy this by going kubectl apply-f manifest. When we do this, you'll see that it created our Tracks service, our Tracks deployment, our lap times deployment, and our web app. And as we can list them all here, you can see all of those containers are running. I have 3 replicas of every single one, meaning these applications are automatically highly available. And Kubernetes is going to make sure that there's always 3 versions of them running at any given time. I can also see that I have my lap time service, my track service, and my web application service. And you'll notice in here on the web application, it actually automatically gives me the DNS record for that load balancer. So if I wanted to load this page up, I can go over to Chrome, and I can see that we now have an application that uses the tracks API to load this list on the side. And each time you click on it, it makes a request to the lap times API to get how those tracks actually happened or how those races actually happened. Now you can see by deploying this application, it made all of that possible. And if we wanted to, we could do things like scaling those automatically. For example, we could do kubectl scale web app 4. Oops. And now you'll see that if I go list the pods again, you'll see that web app actually has 4 replicas now, and one of them was joined 6 seconds ago. So again, we can go back over to the Chrome instance and we can reload this and everything still works. We can also go back and scale these down, for example. If we don't need that many of them, we could scale this back to 1. And you'll see that those containers are now going through a terminating state, so we only have 1. So just by deploying this cluster, we're easily able to deploy our applications into it, set up an ingress mechanism into those containers, and expose them to the world, allowing traffic to get sent in. Going back to the presentation. What's next? If you want to get started, check out the aws-amazon.com/EKS for our Getting Started guide. If you're interested in taking a look at the EKS roadmap and where we're going with the service, we have a fully public roadmap on GitHub that you can influence by filing issues and commenting on existing issues. Or if you'd like to deep dive into how to run containers and applications on EKS, we have a wonderful workshop at eksworkshop.com. Thanks.